Okay, so Lainey, I see your question. Did I not give you a place to turn in the chapter 17 outline? Oh, okay, I'll do that tomorrow. I'll put it on tomorrow's, okay? Sound good? Thank you. I didn't realize that. I thought I put it on the test day. Oh, maybe I just put the chapter 6 questions on the test day. Oh no, it would have been the next day. I don't remember. I'll go back and check and then I'll let you know tomorrow. How's that sound? Okay. Good afternoon. Happy Tuesday, everybody. Okay, so I see some good definitions of entropy. Yes, it's the measure of disorder in a system. Some measurements of entropy can predict spontaneity. Not all of them can. There's 3 different types of entropy, and only one of them can predict spontaneity. Can anybody tell me what the 3 types of entropy are? I'll give you a hint. Entropy of the system is 1. Entropy of the surroundings is 2. And when you add those 2, what do you get? Entropy of the universe. Yes. Nice, Callie. Yeah, so those are the 3 different types of entropy: system, surrounding, and universe. Only one of those can predict spontaneity. Anybody know which one we can look at and tell if it's spontaneous or not? I'll give you a hint. It's not entropy of the system. I'll give you another hint. It's also not entropy of the surroundings. Yeah, it's entropy of the universe. Keep guessing, Cyrus. You'll get there. You're doing a great job. Yeah, entropy of the universe. If entropy of the universe is positive, then you're describing the second law of thermodynamics, which I think I cover on the video today, which is the entropy of the universe increases with a spontaneous system. So it has to be entropy of the universe. If it's positive, it means whatever the process is going to be spontaneous. And no worries if you're not like rock solid on that. The video for tonight just goes over the 3 types of entropy in more detail. Like that's the whole video. So last night's was kind of like an introduction, and then we'll get more in depth tonight. Okay. Second part of the warm-up. Describe the potential energy and probability, like positional probability, of a crystal of sugar and a cup of water before and after they're mixed. Okay, so before they're mixed, you have a crystalline structure of sugar, and you have a like glass or a beaker of liquid water. So a crystalline structure of sugar is very organized. It's extremely organized. It's one of the most organized. A crystal is one of the most organized structures in the universe because all the little things inside the crystal, in sugar's case, it's going to be molecules. At every point in the lattice, you have a molecule of sugar. So they're all a specific distance apart. They're at very specific angles. That's what makes a crystal so beautiful. It's so strikingly beautiful because there's so much order inside it. It has very distinct angles. It reflects light in a very repetitive way. It's very consistent. So a crystal of sugar would have a very low entropy. So low disorder, high organization, basically. And it would contain a lot of potential energy because because you had to basically, I don't know if I want to say this because it's a little deceptive. I won't say it. Okay, the cup of water has less order. It's more disorganized because it's liquid. It's constantly in motion. The distances are variable. They're flowing past each other. There's a lot more positional probability available to a liquid. The crystal only has one way to be organized, right? So there's very few options that the sugar molecules can be in and still be in a crystal. So there's a very low positional probability for a crystal. For the cup of water, there's a lot more options, a lot more positional probability, a lot more disorder. So the question is, when you mix them, does it become more ordered or less ordered? That would be the question. Anybody want to take a stab? When sugar and water is mixed, does it become less ordered or more ordered? Okay, so I see some good processes happening here. Yeah, it's definitely going to be less ordered than the sugar crystal itself, right? So sugar as a solid versus sugar as an aqueous solution is going to increase in entropy, increase in disorder. So what about the water is kind of the process that I see you guys working through on Pear Deck. What about the water? So the outline that our book gave us makes a distinction between electrolytes and non-electrolytes. So do you guys remember what an electrolyte is? An electrolyte is something you can dissolve into water and it'll break into ions, right? It'll support a current because there's ions present. So that would have to be an ionic compound. Any soluble ionic compound is going to break into an electrolyte. So what the book told us was electrolytes are actually going to they could possibly order your solution, or they could not. So if they just tell you that you just created an electrolyte system, you can't really say if entropy has increased or decreased, because depending on the electrolyte, it could go either way. But with non-electrolytes, like polar covalent molecules that are not ionic molecules, they will dissolve, but they won't break into ions, right? So polar covalent molecules that dissolve and create a solution, the solution is going to increase in entropy. It will be more disordered than either the crystal or the water was. So it's a general principle. It's not always true, but it's true enough to be useful for us. So whenever you encounter a polar covalent molecule that dissolves in water, you can assume that the aqueous solution is going to increase in disorder. It's not going to be a very ordered solution because the forces between the polar covalent molecule and the water just aren't strong enough to order it very highly. And now you have all this increased positional probability. You have even more ways to organize the solution now that the sugar's in it. And so positional probability has gone up, so entropy has gone up. Ooh, these are thinking concepts, right? If you don't love math, you may love abstract concepts. So some of you may be in your sweet spot right now. If you do not love this, then you may be more of a math person than you think you are. This is some abstract stuff. Okay, so again, take heart. You're not just going to get hung up to dry after last night's video and be expected to be able to handle all of this. Tonight's video is going to go over entropy again from the perspective of from the three perspectives: entropy of the universe, entropy of the system, entropy of the surroundings. But with that in mind, we can certainly address questions that came up in last night's video. Does anybody have questions? Or things that were confusing, concepts you'd like to talk through a second time, definitions you'd like.
We can just go over entropy of the universe again.
Like a definition of entropy of the universe? Yeah, okay. So entropy is disorder, right? And entropy of the universe is made out of if you take entropy of the system and entropy of the surroundings and you add them together, that describes entropy of the universe. It's kind of like energy. If you have energy of the system, energy of the surroundings, it makes up a total energy. That's
entropy of the universe is just net entropy.
So you do have to specify entropy of the universe because as we go on in this chapter, we'll talk about how entropy becomes part of a bigger picture. Entropy combines with something else to create our third concept called free energy. And at that point in time, they totally drop off the subscript of entropy, and you have to assume that any entropy without a subscript is actually entropy of the system, which seems crazy at this point in time, because at this point in our lives in chapter 17, entropy of the universe is by far the most important one. But as you move into free energy, actually entropy of the system becomes more important than the other two. So yeah, if you're ever talking about entropy, make sure you use a subscript. And if they don't give you a subscript on it, they're talking about the system. Does that answer your question? Yeah, okay. Yeah, so the universe really is as big as it sounds. I mean, they are talking about your crystal plus the liquid it's in, plus the beaker, plus the counter, plus the room, plus the trees outside your room, plus the earth, plus all the things on the earth, plus the other planets and stars in space. Conceptually, they are thinking of the whole universe, which helps us to make a distinction between probability and heat flow, actually. And that's one of the distinctions we talk about in the video tonight. So entropy of the universe is actually entropy of everything. It's like the total disorder once your process has happened. And positive means your system is spontaneous, and a negative entropy of the universe would mean your system is not spontaneous, but the reverse is.
So I thought negative free energy was spontaneous.
Yeah, it is. That's true. That's true. And we haven't talked, as a class, we haven't talked about free energy yet, but you did read about it in your book. So once we get to the end of the chapter, you'll see that there's really two things we can look at to talk about spontaneity. You can look at entropy of the universe. And if you calculate entropy of the universe to be positive, your system's going to be spontaneous. But you can also look at free energy. And if free energy is negative, the system is spontaneous. So it goes to say that if entropy of the universe is positive, free energy is negative. And if free energy is negative, then entropy of the universe is positive. Those two go hand in hand.
Got it.
Was that enough of a summary, Cyrus, or did you? Yeah, okay. Other things you kind of want to recap. I want to make sure you guys have time to ask your questions off of this stuff because it's just so, I feel like it's a lot of very new concepts. Okay, can you go over the different arrangements and what those means, like the probability stuff? Yeah, okay. So one way to talk about disorder is to talk about the different ways things can be ordered. So the probability is easier to understand with a very simple system. So okay, so let's step away from the gas molecules for a second and talk about cards for a second. So if let's say we take 2 playing cards. Let's do the Queen of Hearts and the Queen of Diamonds. Okay, so we have 2 playing cards, and you can put these playing cards into a deck, right? So the question would be, how many ways can you put these playing cards into a deck? So think about that for a second. How many different ways can you put these playing cards into a deck? Okay, so if they're both facing up, there's 2 ways, right? Hearts on top or diamonds on top. But if you can flip them upside down, there's more ways. Okay, upside down, hearts on top, upside down, diamonds on top. Or hearts up on top, facing up, diamonds facing down. Vice versa, diamonds facing on top, facing up, hearts facing down. Or you can flip them, hearts facing up on bottom, diamonds facing up on bottom, the other one facing down. So there's like 8 different ways you can order these, right? If you just throw them in the air and you pick them up and put them into a pile, there's really 8 ways that these can be ordered. Okay, so what if you just have 1 card? How many different ways could you order it? Two ways, right? If you just have the Queen of Hearts, it could be face up, it could be face down. So there's 2 different ways you can order 1 card. With 2 cards, there's 8 different ways you can order it. What about with 3 cards? Anyone good at stats? I am also not fantastic with stats, but I think it's something like 27 ways you can order it. And so as you see, like the ways to order cards become exponentially larger, right? If we throw another queen in here and we go Queen of Spades. Oh, that was not a fantastic spade. That was more like a lollipop. Okay, there we go. There's our spade. Okay, if we throw a Queen of Spades in here and we throw them up in the air and we pick them up, there's a bunch of different ways you can order these, maybe 27 different ways. Okay, so this is what the molecules are getting at. If you have 2 gas molecules, the probability of finding the molecules in the left side, if you have 1 molecule, okay, there's really only two ways that one molecule can be ordered. If you have two molecules, there's 8 ways those two molecules can be ordered, right? There's a fourth of a chance you can find it over here. You can find one over there and the other one's going to be here. There's a fourth of a chance you're going to find them together. There's a fourth of a chance you're going to find them flipped. And then there's another fourth of a chance you're going to find it over here. So to find them both in the left column would be 1/4 for the red, 1/4 for the blue, something like that. 1/4 squared. I don't really know. Comes out to be 1/8 somehow. Again, stats is not my forte. If you put a third molecule in here, then the amounts of positions that you could possibly find, the ways you could orient it, just get exponentially bigger. I think 3 is going to be a 27. So every thing that we throw into the system makes our possibilities of the ways that these things can order themselves inside the system just bigger and bigger and bigger and bigger, right? Every card we throw into our pile, we throw up in the air to pick it up, just gives us more options of how we can pick it up. So if being ordered is a very specific thing, okay, for the cards, being ordered means you have a heart and then a diamond and then a spade. And anything other than that order is going to be considered disordered. So there's a lot more ways you can pick up the cards and have them be disordered than there are compared to your one way to order it. And the same is true for gas molecules. If both of the gas molecules being on one side is your ordered scenario, there's a lot more ways you can be disordered than that one way you can be ordered. Same thing with a glucose molecule, for example. Imagine taking, what's glucose? C12H11O22, something like that. No, that's not right. Let's just say we'll go sucrose. Something like that. Think if you take 12 carbon atoms, 12 hydrogen atoms, 12 oxygen atoms, and you just let them go and bond, you're not they can bond in a lot of different ways and not come out as glucose, right? So in order to get glucose to form, that's a very improbable scenario unless you have a mechanism that takes carbon and attaches it to hydrogen and takes carbon and pulls off the oxygen and reattaches it in another place. And that mechanism is called a plant, right? A plant is a mechanism that orders this molecule to come out in a very specific way. But if that's your definition of ordered, there's a million other ways that it can be disordered. So if you think about the glucose breaking down into its components, which is what your body does, your body takes acid and attacks this molecule and pulls off the individual atoms and sends them on their way, right? Or pulls off pieces of the molecule and sends them out to be used. There's a whole lot of ways for that to be disordered. And so our systems naturally move towards disorder. In order for a system to move towards order, we need a mechanism and an input of energy. So what's the input of energy that creates glucose? It's the sun, right? The sun is the increase of energy, input of energy. The plant is the mechanism. And so this is what we're talking about. There's just a whole lot more ways that something can be disordered compared to the one way it can be ordered. So when you throw up a deck of cards, you're not going to pick it up in order. You're just not. It's statistically not probable, right? Sure, it's not impossible, but tell me one person on this earth in the history of time who's ever thrown up a deck of cards and picked them up perfectly in order. There's just too many different ways it could be disordered compared to that one way it could be ordered. And so nature is going to move towards those disordered states, not towards the ordered states, not unless you have a mechanism and an input of energy. So how would you describe probability when the molecules are not in a tube like that? Right. So the reason we put it in the tube like that is because it gives you very specific conditions that we can define order by. So when you remove the tube, the conditions just become far more complicated. And so that's why we put all these parameters in place. Like if a solid becomes a liquid, that's an increase in disorder, right? The solids have very specific distances and very specific angles to one another. That's a lot of order. Liquids have variable distances and they move past each other. That's less order. So going from a solid to a liquid is an increase in disorder. Likewise, liquid to gas, also an increase in disorder. An input of temperature will give you more speed and more movement. That will increase disorder. What else was on that list? Dissolving, creating an aqueous solution with a polar covalent solid, increase in disorder. So because all the other systems are just so much more complicated, we need definitions to define this entropy or this disorder by. So as far as positional probability goes, they give you those guidelines. Solid to liquid, liquid to gas, increase in temperature, dissolving a polar covalent solid. Those things will increase your entropy because everything else is just too complicated of a system to think about, right? And then you'll see in the video tonight, they also talk about the movement of heat. And the movement of heat can also define disorder for us. And that's kind of the temperature component, right? So as energy enters a system, it's going to give it motion, which makes it more disordered. As heat leaves a system, it's going to decrease motion and make that system more ordered. So you're right, Callie. It's just so complicated outside of that little tube that we need to work within these parameters. We need to establish these parameters and think inside of them, basically. It's a crazy concept. Does that help? Was that too much explanation? Any other questions? Or should we just try some problems? Okay, I see nodding. Let's try some problems. All right, here's one. Okay, this was similar to the one that was in the notes, but it's different contexts. So try this one and see how it goes. I also accept questions, so answers or questions is fine to put in. All right, I'll give you 30 more seconds, then we'll talk about it. Okay, so I see a question. Where would I start? So on these, you're going to have to go to those definitions we talked about. Is there an increase in, is there a transition? What's the term I'm looking for? Going from a solid to a liquid to a gas. Is there an increase or decrease in molecules of gas? Is there like a transition of heat, an exchange of heat? Is there, are you going from are you creating a solution? Those are the kind of things you're going to have to look at for these problems. And the first one, notice that they're all gases. They're just being rearranged except for this one. This one's a liquid. So you're actually going from 3 moles of a gas to 1 mole of a gas. And so that is going to decrease disorder. So entropy is going to be negative there. On B, you're dissolving methylamine in water. So you're creating a solution going from a solid to an aqueous, right? But the question is this going to be an electrolyte solution or not? If it's an electrolyte solution, you can't answer that. It may increase in entropy, it may decrease in entropy. But if it's a polar covalent molecule, you should be able to tell me the change in entropy. So methylamine, is that going to split into ions or not? And it would not, because it is not an ionic compound. It's an organic compound, and organic compounds don't split up into ions. And so this one, you should be able to tell me that entropy is going to increase. It's going to get more disordered. And then sublimation of carbon dioxide, you're going from a solid to a gas. It's a phase change. That was the term I was looking for like a minute ago. Phase change. Solids are ordered, gases are less ordered. So entropy is going to increase. So your answer should be decrease, increase, increase. Questions, comments, concerns on that one? Okay, on the next one, here we go. Which of the following processes involves the greatest increase in entropy? And go. All right, and the answer on this one is E. E is the answer on this one. A goes from 2 molecules of gas to 2 molecules of gas. B goes from 4 to 2. So that one, entropy doesn't change on this first one. Entropy actually decreases on the second one. C is tricky because it's ions going to a solid, but it's an aqueous ions going to a solid. So you really can't say either way because you're going from an electrolyte solution to a solid. So it may be decreasing in entropy because you're forming a crystal, but maybe not because an electrolyte solution is pretty ordered also. On D, you're going from 3 molecules of gas to 1. So entropy here is going to decrease. And then on this last one, you're going from a solid to 1 mole of gas. And so this is actually the only one where entropy is going to increase for sure. Any questions on that one? So really, we're just dealing with this conceptually right now. And the whole idea really comes back to kind of those like 4 or 5 different postulates. Phase changes from a solid to a gas. Gases are going to be more filled, more disordered, right? Less moles of gas to more moles of gas would be an increase in disorder, increase in temperature, and then creating an aqueous solution from a polar covalent molecule. We're really seeing this practice operate off of kind of those, like that little box of definitions so far. Okay, and then we're getting to the second law of thermodynamics. And so here is where we start to look at the 3 different types of entropy. And we're going to kind of break down the definition according to the 3. So that is tonight's video. So how do we feel about this so far? Are we okay? Are we super confused? Give me a rating, like 0, I'm super lost. 1, I kind of feel more comfortable after doing practice, but I'm still not super confident. Or like 2, yes, Martins, I have this. Let's just move on with life. Okay, that's fair. I think also, like, as we define this better, you're going to feel more comfortable with it as we kind of like build the definition out bigger. So if you're at a 1, that's a decent place to be. If you're at a 2, then great. Let's just keep rolling. Okay. I'll hang out if anyone has questions or things you want to talk about. If you dare ask me, I feel a little rambly today, so I'm here. Otherwise, have a great afternoon. I'll see you guys tomorrow. Bye.